where we want to test the difference between two means where we have dependent samples. So here we want to compare means by using a method that we call a paired sample technique. A paired sample may be appropriate when the members of the two populations have a natural pairing. Each pair in the paired sample consists of a member of one population and that member's corresponding member in the other population. I have no idea what that bullet point is supposed to mean, to be honest with you, so we'll have to edit this part out. In other words, the idea is you have a person that is in one population and you have the same person in another population, is basically what we have going on here. So let's just take a look at this example. I think this example will kind of bring a little bit of light into our thought processes here. So this is the example that I talked about the other day. So as an aid for improving student study habits, 9 students were randomly selected to attend a seminar on the importance of education in life. The table shows the number of hours each student studied per week before and after the seminar. So at alpha equals 0.1, did attending the seminar increase the number of hours the students studied each week? So here the idea is that we have a population that is the before, so I'll call this X1, and we have a population that is after, and here I will call this X2. So the idea is that if I have this before population and this after population, notice that each member, so each column of numbers here, represents the same person in the before population and the after population. So that's kind of the idea that's going on. Notice that if you look at these, again, as two different populations, you have the same person in a before and an after. Pre-test, post-test. Left foot, right foot. Okay. So that's the important thing, is to notice between the other examples we were working on earlier, is that we had two independent populations where there was not a similar subject in both populations. Both populations were independent. They didn't have anything in common. So now I still want to continue working with this example and to kind of shed some light as to where we're going to be heading. So let's take a look at each one of these, and notice that we are asked if attending the seminar increases the number of hours that the student studied per week. So if we wanted to know if this intervention program worked with these students, all right, then what would we expect in comparison between the before and the afters? If we were to review all of these numbers here, if the intervention worked, what would we expect with these numbers, with these two different populations? We would expect increased study time in which population? In the after. So if the intervention worked, then we would expect these numbers to be larger than these numbers up top, right? What if the intervention didn't work? Then what would we expect with the numbers in both of these populations? They should be relatively close or the same. So when we want to compare two different numbers with the same subject here, how can I do this comparison? What have we been doing all semester long when it comes to do a comparison? Almost. There's one thing we have to do first.
The null hypothesis?
No, not the null hypothesis. Okay, let me. All right, let's go with the idea that the seminar did not work. So we just said that these numbers should be pretty close. How can I tell if these numbers are going to be pretty close? What could I do? Other way. Other way. Subtract them. Right? So if I want to know if the seminar did not work, then I would think that these two numbers would be fairly close to one another. And in fact, and if I want to determine if they are close to one another, then shouldn't I take their differences? All right, now let's still run with this premise that the seminar didn't work now. If these numbers are going to be close to one another, then what would I expect the differences to be close to? 0. All right, so let's take a look here. So here I have 0, -5, -3, -5, 1, -3, -5, -9, and 1. So again, working on the idea that if the seminar did not work, then I would expect these numbers to be close to 0. Or another way I could look at it is I could take these differences and then I could take the average of these differences, and what would I expect the average to be close to? 0. Now, if the seminar did work, and I took these differences just like I did, if I thought the seminar, now be careful, if I thought the seminar did work and I take these differences, then what would I expect a lot of these differences to look like? That is, what values would I expect these things to look like? I would expect to see a bunch of negative numbers down here, and the reason is because we said if the seminar worked, that means that the after population should be larger than the before population. Right? Or if I wanted to know if the seminar didn't work, then when I take these differences, then I would expect my differences to be positive. So there's not working, no difference, and then there was a difference. The seminar did work. We can look at it that way. So again, if the seminar did not work, then when I take these differences before minus the after, then I would expect these numbers here to be large, positive. Not large, but positive. If the seminar had no effect, then I would expect to see these differences to be close to 0. If the seminar did work, then I would expect these differences to be negative. Okay? We're going to keep that in mind here as we continue on. We're going to come back to this. All right, so suppose that X is a variable on each of the two populations whose members can be paired. Basically, the idea is that you have a dependency, so the dependency depends on if the subject is in both populations, if you will. The before and the after, pre, post, or whatever. You have another way of thinking of this is maybe the same subject on two different treatments. In other words, when we go back and look at the student intervention, there was the treatment where there wasn't an intervention, and then there's kind of a treatment where there is an intervention, and we want to see if it works. So we have the same person going through both treatments, if you will, and I'm using the word treatment very loosely, not like what we talked about in Chapter 1. So now what we'll do is for each pair, we will let D denote the difference between the values of the variable X on the members of the pair. So going back here, these guys right here, these are my differences down here. So we will let D, we will call D the paired difference variable. It can be shown that the mean of the paired differences equals the difference between the two population means. That is, that the mean of the differences is going to equal to the mean of the first population minus the mean of the second population. So the idea is that if I could compute the mean for the before and compute the mean of the after, or if I knew the population means here and the population means here, and I take the difference, that should be very close, that if I compute the mean of the differences here, if I knew the distribution. Okay? Furthermore, if D is normally distributed, we can apply this equation and our knowledge of the studentized version of the sample mean. So again, the idea is that we have a small sample, we have the differences. If the differences are normally or approximately normal, then we know that when we go to talk about a test statistic, and we know that when we go to do all of that stuff, that our test statistic based on the data, based on the X bars, based on the standard deviation, should follow an approximate t distribution. This is everything that we've talked about since chapter 9, small sample case. Basically, this is saying the same thing on the differences, though. On the differences. Okay? So just to go one more step, suppose that X is a variable on each of the two populations whose members can be paired. Further, suppose that the paired difference variable D is normally distributed, then for paired samples of size n, the variable T, which is equal to D bar minus the mean of the differences, and I should subscript this with a sub-zero. Again, this is going to be under the null hypothesis, divided by the standard deviation of the test statistic here, or of our sample statistic, D bar. So again, inverting and multiply for computational purposes, this is going to be our standard, our studentized T test statistic, where we have degrees of freedom is n minus 1. So this D bar is going to be the mean of the pairwise differences, and S sub D is going to be the standard deviation of the differences. So these D bar and S sub D, when we have the data, is going to be something that we're going to have to compute. So that forms our foundation